The Center for Theoretical Physics is a fantastic place to do research because I have colleagues who have expertise in so many different areas.
There's a lot of interdisciplinary conversation and collaboration.
Very interactive environment. With the current setup, with this nice new space that we have, there is great opportunities for interaction with people. This just seems to happen naturally at the CTP. I mean, it's the space, but it's also the people. I'm Will Detmold.
I am Tracy Slatcher.
My name is Jesse Thaler. I'm a particle physicist working on dark matter at the MIT Center for Theoretical Physics. One of the proposals that I'm really excited about for chasing dark matter is an experiment that has the name Abracadabra. Abracadabra is an actual acronym. It stands for a broadband or resonant approach to cosmic axion detection with an amplifying B-field ring apparatus. That is perhaps the longest legitimate acronym in particle physics. And this is an experiment that's using a precision electromagnetic device to try to listen in to ripples of dark matter that might be going through it. One of the great things about working at the MIT Center for Theoretical Physics is that if you have a new idea for how you might detect dark matter, you can go down the hall to your friends in the Laboratory for Nuclear Science, and they have all the equipment you might need to make a discovery. Well, hi Lindley, it's really great to see Abracadabra here in the flesh. And I remember coming to your office a while back and drawing for you on the chalkboard a precision electromagnetic to catch dark matter. And you said that this is a really cool idea, but it would take a little bit of work to make it actually happen. And so I'm excited to see what you've made of this idea, Abracadabra.
Right, so because the signal that you predicted was so small, at sort of room temperature, just electrons moving around thermally will mimic the signal. So this whole thing had to get cold. And thankfully, and the reason you came to my office, was that I had this refrigerator already here. This of course is the world's fanciest refrigerator, in that it can cool things down to 10 millikelvin, a fraction of the temperature of free space. And then the problem is, how do we actually get the signal out that you were expecting? So because the signal's so small, we need to shield radio stations and everything else that's making noise. And so what this is here on the outside is a superconducting shield. It's basically two bowls of copper that have been spin coated in tin. And when they get really cold, they go superconducting and they'll block everything else out. So then the next problem was getting the signal out. So it does have two little holes here for bringing out the signal. And the signal goes to some very sensitive current sensors. Then the signal is coming out of here. And so once this whole thing's cold, we power on the magnet and we look for signals.
How big is the actual real toroidal magnet inside there?
So it's 12 centimeters, so it's about that wide.
So it really actually fills the entirety of the shield.
It really is fitting in there, sort of like a bundt cake.
But there's even discovery potential with this small prototype.
And I'm an optimist. I think we could discover dark matter next week.
My research with Will actually overlaps, where both of us have an interest in understanding dark matter, with my interest focusing on what dark matter might be, and Will's calculations being relevant for figuring out how dark matter might interact with the standard model.
Dark matter is one of the greatest mysteries in physics at the moment, I think. In terms of my research, I'm spending a lot of time thinking about ways of doing the calculations that I need to do to provide the input that these dark matter experiments will need in order to understand their detections when they see dark matter. At MIT, there is a very nice facility, the Bates Lab at Middleton, Massachusetts. And so there I have a small cluster of computers that are actually pretty instrumental in my research, because having direct access to this resource means that me and my group can try out new ideas with minimal overhead of getting things going. And so this has really been instrumental in pushing forward new ideas.
Yeah, so previously you had mentioned this hard
When you
space.
think about what other CTP faculty are doing, there's also a lot of computation being done. For example, Tracy spends a lot of time looking at data coming from satellites, and understanding and processing that data is a fairly substantial computational task.
Dark matter is a puzzle. We have pretty good reason to believe that about 80% of the matter in the universe is dark matter. We know that it doesn't interact very well with light at all. We believe that the cosmic structures that we see today started to form when, in the early universe, dark matter began accreting into small clumps. In these halos of dark matter, there was a lot of mass, so there was a lot of gravitational attraction, and ordinary matter was increasingly drawn into the centers of these halos. So ordinary matter started forming stars, Eventually, planets form. But the dark matter is still just out there, forming the scaffolding for the galaxies, planets, the gas clouds, everything that we know of within our galaxies and other galaxies is sitting on top of that invisible backdrop of dark matter. A few years ago, my collaborators and I began to look at the region around the center of the Milky Way. What we found was this mysterious glow of gamma rays that extended outwards from the galactic center, and we were for a while very excited about this as a potential signal of annihilating dark matter particles. But then we found that actually this glow might be telling us that there's a new population of stars emitting gamma rays. We think that they're pulsars, which is spinning neutron stars, which produce beams of radiation. Occasionally people ask me, are you disappointed about this? You found the wrong thing. No, I mean, it's a discovery. We just learned something about our Milky Way that we didn't know before. This is how science goes, and I, for one, am very happy about it.
One of the things that I learned early on when I joined the CTP is that if I just leave my door open to my office, there will be a flood of people and ideas coming in.
I think there are a ton of potential discovery channels open. I think the next several years will be an enormously exciting period.
I mean, I think the faculty that we have are very open to discussing things outside their area, and I've found it to be a great environment.